Why waste time in commute and spend lot of money for iitjee coaching? Parents, do you want your kids to achieve top scores in iitjee? India's leading online NEET coaching 100% success iitjee. At TeenEinstein, we focus on iitjee coaching from class 6 to class 12. We think you'll like it. Our teachers are mostly PhDs in physics, maths, chemistry, botany, and zoology, with lots of years of teaching experience for class 6 to class 12. Thousands of videos, quiz, MCQs. We provide a daily worksheet of 30 questions on each topic: math, physics, chemistry, and biology, for rigorous practice, concept understanding, evaluation, quiz, and thousands of videos. Limited offer 40,000 rupees per year. Book your class. TeenEinstein.com.
Hello everyone, welcome to this video. In this video, we are going to talk about electromagnetic induction. In the previous videos, we discussed how a moving electric charge can produce magnetic field. So in this video, we are going to see the opposite of this phenomenon, where a changing magnetic field is going to create an electric field. So let's start the lecture with an introduction. Then we will move on to the experiments of Faraday and Henry which led to this discovery. Then we will talk about what is magnetic flux, then Faraday's laws of induction, Lenz's law and conservation of energy. Then we will talk about what is motional EMF, then how it is helpful in energy consideration, eddy currents, inductance, and AC generator. So we already discussed this. So far, we were thinking that electricity and magnetism were a separate phenomenon. So we have known electricity for so many years and magnetism separately for so many years. And then in the early decades of the 19th century only, experiments on electric current by Oersted, Ampere, and a few others established the fact that electricity and magnetism are actually interrelated. They found that moving electric charges produce magnetic fields. For example, an electric current deflects a magnetic compass needle placed in its vicinity. So we discussed this in detail in the last lecture. So if an electric current can deflect a magnetic compass needle, is the opposite also possible? Is the converse effect also possible? Can moving magnets produce electric current? So this experiments of Michael Faraday in England and Joseph Henry in USA, conducted around 1830, demonstrated conclusively that electric currents were induced in closed coils when subject to changing magnetic fields. So this phenomenon is very, very important. This discovery is very important in the history of science because you see all the electric motors function based on this, and also all the electric generators function based on this. So when I say electric generators, this is the principle with which we are producing electricity. So this is a very important one. So this particular phenomenon in which electric current is generated by varying magnetic fields is appropriately called electromagnetic induction. So this particular phenomenon is called electromagnetic induction. Generators and transformers work based on this principle. So we know what are generators. These are electricity generators. So these are the generators are there in like a cycle dynamo, or also if you think in a bigger picture where you produce electricity, mass electricity, right? So by using in the hydroelectric power plants where you use the water that is coming down a dam to produce electricity. So in this kind of instruments and generators, this particular electromagnetic induction is used. And also transformers, we know transformers are used to step up or step down the voltage, and transformers are also very important in everyday applications. Okay, so we are going to see three experiments which led to this kind of a discovery. So we will start with the first experiment of Faraday and Henry. So figure shows a coil C1 connected to a galvanometer G. So this is a coil C1. Look at it, it's a closed coil and it is connected to a galvanometer G. So what does a galvanometer do? It shows you if there is a current in the circuit. Okay, it deflects when there is a current in the circuit. So when the north pole of a bar magnet is pushed towards the coil, the pointer in the galvanometer deflects, indicating the presence of electric current in the coil. So there is a magnet here if we move this magnet towards this coil, you see there are this magnetic field lines just going inside. So they are getting cut by this coil basically. So whenever you move this magnet towards the coil, then they are seeing a deflection in the galvanometer. It indicates that there is an electric current in the coil. And the deflection lasts as long as the bar magnet is in motion. The galvanometer does not show any deflection when the magnet is held stationary. So once you start moving and then you stop after bringing it here, then the current stops. So only when the magnet is moving, there is a current. When the magnet is pulled away from the coil, the galvanometer shows deflection in the opposite direction, which indicates the reversal of the current's direction. So this is an important point. When you move it in the opposite direction, then the current's direction is also changing. So this is about experiment 1. And then what are the observations we had? What if we change the pole of the magnet? So when the south pole of the bar magnet is moved toward or away from the coil, the deflections in the galvanometer are opposite to that observed with the north pole for similar movement. Further, the deflection is found to be larger when the magnet is pushed towards or pulled away from the coil faster. So if you move the magnet faster, the deflection is larger. So it means that the amount of current produced is also larger when the magnet is moving faster. So instead, when the magnet is held fixed and the coil C is moved towards or away from the magnet, the same effects are observed. So what are we concluding from these observations? The relative motion between the magnet and the coil that is responsible for generation of electric current in the coil. So this is the overall conclusion which we are arriving at from the experiment. So the relative motion is very important. I mean, the bar magnet has to be in motion compared to the coil. If both are moving with the same velocity also, there won't be any change. So with respect to the coil, the bar magnet has to be moving. Then only they saw a change in the galvanometer position. Okay. Now let's move on to the experiment 2. In this experiment, what we are going to do is we have the same setup from the first experiment. C1 a closed coil attached with a galvanometer which shows a deflection if there is a current. But instead of a bar magnet, we have a current carrying coil called C2. So the C2, if you see, there is a battery attached to it. Unlike this, where there is only a galvanometer, there is no power source. So in this case, there is a battery attached to it. So there is an actually current in this. So why we have this, kept this? Because in the last lecture, we studied that a current carrying coil will act as a bar magnet. So instead of a bar magnet, we are just replacing it with a current carrying coil. Now what happens? Let's see. As the coil C2 is moved towards the coil C1, the galvanometer shows a reflection, just like what we saw in the previous experiment. So there is an electric current induced in C1 because of this movement. When C2 is moved away, the galvanometer shows a deflection again, but this time in the opposite direction. This deflection lasts as long as coil C2 is in motion. When the coil C2 is held fixed and C1 is moved, the same effects are observed. Conclusion is the relative motion between the coils induces the electric current. So this experiment is exactly similar to what we observed in the bar magnet. So this kind of confirms our results from the first experiment. So in this case, just instead of a bar magnet, we have a current carrying coil which produces the similar magnetic field. Okay, let's move on to the third one. In the third one, actually, we have a similar method where we have the same C1 with a galvanometer and a C2 with attached to a battery, and there is a key attached to it. So what does a key do? When you close the key, the circuit completes and the current starts flowing in the circuit. When you open the key, then the current stops flowing because it's not a closed circuit anymore. Remember in the previous slide itself, we saw that it should be a closed circuit to current to pass, right? So this is the setup. Now let's see what happens. It's observed that the galvanometer shows a momentary deflection when the tapping key K is pressed. The pointer in the galvanometer returns to 0 immediately. So when you press the key, the current increases from 0 to, let's say, I. So when the current is changing in this circuit, in this particular circuit, there is a current induced here, the galvanometer shows a deflection. So right now they are not moving this coil, they are just keeping it stationary, but they are changing the current in the second circuit. Look at this, if you change the current in the second circuit, just you change the current in the second circuit, it induces a current in the first circuit, right? If the key is held pressed continuously, there is no deflection in the galvanometer. When the key is released, the momentary deflection is observed again, but in the opposite direction. So what do they mean by when the key is released? You open the key, so you are again reducing the current from I to 0. So in both these situations, whenever there is a change in current only, then you are seeing a deflection in the galvanometer. So what do I mean by change in current? When the current is changing from 0 to I or I to 0, then you are seeing a change in the galvanometer attached to the first coil. So it's also observed that the deflection increases dramatically when an iron rod is inserted into the coils along the axis. So if you insert an iron rod here, the deflection increases dramatically. So it means that the current is also increasing dramatically in the first coil. Okay, so now we have completed this experiments. So before going further into electromagnetic induction, we need to understand what is magnetic flux. So we have studied what is electric flux already, and we defined it as E multiplied by A. So E is the electric field strength and A is the area. So flux is nothing but the area multiplied by the electric field strength. It's a vector product, dot product of two vectors. So similarly here also we are going to define the magnetic flux phi as B dot A. So B dot A is BA cos theta. And you see if this is the surface and it makes an angle theta. So the A represents the direction of the surface and it makes an angle theta with the magnetic field direction. So if the magnetic field is like this and A is like this, then what is the flux? Flux is given by BA cos theta, theta being the angle between B and A. So now let's say we have a complicated surface, not so simple like this one. So in this case, what do? We divide the surface into small pieces like this, each with an area of dAi and with a magnetic field of Bi. And then we take the product of this, dot product of this, and sum up for all the areas, all the small area elements. So that's what is shown here. Phi b equal to B1 dot dA1 plus B2 dot dA2, etc. up to Bn dAn, which is equal to Bi dot dAi, which is about all the elements. Then you get the overall flux through a surface like this. Okay, so this is called magnetic flux, and the SI unit of magnetic flux is Weber or Tesla meter squared, and it's a scalar quantity because it's a dot product of two vectors. Okay, now let's see what's Faraday's law of induction. So we know that we saw three experiments, and in all the three of them, we came to several conclusions that whenever we move the magnet, the current is induced. When you change the current, then in the second coil, then there is a current induced in the first coil. So we will just have to put all of them in the form of an equation and see what is happening here. So Faraday arrived at a conclusion that an EMF is induced in a coil when magnetic flux through the coil changes with time. So when he says magnetic flux through the coil changes with time, remember that the flux has two quantities in it. One is the magnetic field and the other one is the area. So in this what we mean by A is the area covered by the coil. For example, in the C1, we had a coil, a circular coil. So the area of that coil only we have to consider here when we talk about the magnetic flux. So Faraday says that an EMF is induced in that particular coil whenever the magnetic flux is changing. So that means it could be that B is changing or it could be that A is changing or both are changing, but they are inducing a magnetic field in the coil. So the common point in all these observations is that the time rate of change of magnetic flux through a circuit induces EMF in it. So the time rate of change is very important because only when the bar magnet was moving, then there was a change in the galvanometer place. So it should have a movement. So that means that the position of the bar magnet has to change with respect to time. When the position of the bar magnet changes, what happens? The magnetic field enclosed in that coil is also changing. So hence the magnetic flux is changing. So EMF is produced. So let's put that in the form of an equation. So epsilon equal to minus d phi b by dt. So phi b is the flux and it has to change with respect to time. Only when this quantity is non-zero, there is an EMF. Then it doesn't survive if it is zero. And why there is a negative sign? The negative sign indicates the direction of epsilon and hence the direction of current in a loop. See, we can understand it this way. It is like an inertia. Everything in nature wants to stay in its own way when you try to change it. Similarly, when you change the magnetic flux, the current is produced in such a way that it opposes the change in the magnetic flux. We will see this further in the next slides. So right now I just want to mention that it indicates the sign of the EMF. And this negative sign indicates where the current, what will be the direction of the current in a closed loop also. Okay, so if you have a coil with many number of loops, then we have n is the number of loops, and the equation is this. So EMF equal to minus n into d phi b by dt. Now let's see what is Lenz law and conservation of energy. So the polarity of induced EMF is such that it tends to produce a current which opposes the change in magnetic flux that produces it. So this is what I was talking about. So when there is an induced EMF, the induced EMF is in such a way that it tries to change the magnetic flux. Sorry, it opposes the change that is already in the magnetic flux. It is almost like it doesn't want the magnetic flux to change. So it induces a current which tries to oppose this change. Okay, so the polarity of induced EMF is such that it tends to produce a current which opposes the change in magnetic flux that actually produced the current. Okay, so the direction of the induced EMF can be found using Lenz's law. Suppose that the induced current was in the direction opposite to the one depicted in figure A. So let's say that in this case, the south pole due to the induced current will face the approaching north pole of the magnet. So the north pole is coming here and south pole of the induced magnet will face the north pole. So the bar magnet will then be attracted towards the coil at an ever increasing acceleration because it's south pole and it's north pole. Now consider the correct case shown in figure B. In this situation, the bar magnet experiences a repulsive force due to the induced current. Therefore, a person has to do work in moving the magnet. So in this case, since this produces a south pole, it attracts the bar magnet. But in this case, it produces a north pole, it repels it. And if you want to push it, then you have to do some work. Okay. Now let's consider a straight conductor moving in a uniform and time independent magnetic field. So this is a uniform magnetic field and it's time independent, and there is a straight conductor moving. There is a straight conductor and it's moving. This figure shows a rectangular conductor PQRS in which the conductor PQ is free to move. So this PQ is free to slide across this. So this loop is stationary. So if you look at this picture, it creates a loop PQRS. So this rectangular loop is produced and along with the current is moving. Current I is going. Now the rod PQ is moved toward left with a constant velocity v as shown in the figure. There is no loss in energy due to friction. Now PQRS forms a closed loop enclosing an area that changes as PQ moves. So like I said, for a magnetic flux to change, you don't necessarily have to change the magnetic field. You can also change the area. In this case, if you see, this PQ is constantly moving towards the left. So what happens? The area keeps reducing, right? So it's placed in a uniform magnetic field B, which is perpendicular to the plane of the system. So if the length PQ equal to S, this is X. Sorry, RQ equal to X. So this RQ is X. and R is equal to L. So this length or PQ or R is equal to L. The magnetic flux phi B enclosed by the loop is given by BLX. Why BLX? B is the constant magnetic field, and in this case it's 90 degrees, so it's basically phi equal to BA cos theta. Since it's 90 degree, we are just keeping BA, and A is a rectangle, so it is L multiplied by X. So phi B equal to BLX. Now let's see what happens. Since x is changing with time, the rate of change of flux phi b will induce an EMF. Now epsilon equal to minus d phi b by dt, which is equal to minus d by dt into BLX. Now b is not changing. L is this length which is constant. So L is not changing. So let's take it out of the differentiation sign. So now what we have, minus BL dx by dt. Dx by dt is nothing but the velocity of this velocity with which the rod is moving towards the left. So now we have epsilon equal to BLV. Since it's moving towards the left, we have put minus V here. Okay, so now the induced BMF is called BLV. It's called motional EMF because it's produced due to the motion of the conductor. We are also able to produce induced EMF by moving a conductor instead of varying the magnetic field. That is by changing the magnetic flux enclosed by the circuit. So we can produce the electromotive force by two different ways, either by changing the magnetic field and keeping the loop constant, or changing the shape of the loop by changing the area and keeping the magnetic field constant. We can do anything in this. Okay, so now let's consider an arbitrary charge Q in the conductor PQ. So there is a current, obviously there will be charges and the charges are moving. So when the rod moves with speed R, the charge will also be moving with speed R in the magnetic field. So when the rod is moving, then the charge is also moving. So the Lorentz force on this charge is QVB. So we know what is Lorentz force. Lorentz force is Q multiplied by E plus VB. So in this case, since there is no electric field in this particular direction, we can neglect E. So we have QVB in the force, Lorentz force acting on the charges, and its direction is towards Q. Now, what they mean by Q, it's towards P to Q. So it is this direction. Now the work done in moving the charge from P to Q is W equal to QVBL. So when this is moving here, so the work done is QVB into L. Since EMF is the work done per unit charge, then we get epsilon equal to W by divided by Q, then we get BLV. So we are just deriving the same equation in another way by using Lorentz force instead of using Faraday's law like we did before. Okay, so now let's look at it from the energy conservation point of view. So we know that an EMF is produced, and where is this energy coming from? So let R be the resistance of movable arm PQ of the rectangle conductor shown in the figure. We assume that the remaining arms QR, RS and SP have negligible resistances compared to R. The overall resistance of the rectangle loop is R, and this does not change as PQ is moved. The current I in the loop is I equal to epsilon by R. So epsilon is the EMF, so EMF produced is epsilon. So the current that is flowing has to be epsilon by R. We are assuming that R is the resistance of this PQ, and we are assuming that this particular length QRSP does not have any resistance. So then current is produced by BLV by R. On account of the presence of the magnetic field, there will be a force on the arm PQ. The force is given by IL cross P. So this we discussed in Biot-Savart law. So the force on this particular PQ arm is going to be IL cross P. Then it is directed outwards in the direction opposite to the velocity of the rod. So the magnitude of this particular force is going to be ILB. Since it's 90 degree, we are ignoring the cross sign here. So then we have F equal to ILB equal to B squared L squared into V. Since we are substituting for I here, so BLV by R, then we get B squared L squared V by R. So this is the force that is exerted on the PQ rod opposite to its motion. Okay. Alternatively, the arm PQ is being pushed with a constant speed V. The power required to do this is, so there is a force acting in the left. That's why it is moving. So what is the power associated with it? It will be force multiplied by velocity. See, energy is force multiplied by the distance, and power is energy by time. So if you look at this, then it should be Fx divided by t. X by t is nothing but V. So we are taking F into V. So now let's substitute this force here. B squared L squared V by R, like we derived before, and then multiply by V. So we have B squared L squared V squared by R. So this is the work done in moving this arm towards the left. So we are doing this work and it's in mechanical form because it's just to move this arm. Okay. So this particular mechanical energy is dissipated as joule heat and it is given by. So where does this mechanical energy go? So when you move this arm, then you're giving some mechanical energy. So this mechanical energy is dissipated as joule heat and it is given by I square into R. So Pj equal to I square into R, which is equal to BLV divided by R the whole square, because we are just substituting for I into R. So what we get is B square L square V squared by R, exactly same as this. So the mechanical energy which was needed to move the arm PQ is converted into electrical energy and then to thermal energy. So this electrical energy induced, the epsilon, is also coming from this mechanical energy, and then what happens to that energy? It gets converted into thermal energy. And we all know what is joule heating, and it's when an current carrying conductor gets heated up, then we call that joule dissipation. So that's what is happening now. So from Faraday, we know that the magnitude of the induced EMF is epsilon equal to delta phi by delta t, and epsilon equal to IR. This is from Ohm's law. So if you substitute what is I, it is nothing but delta Q by delta t. And so delta Q, if you compare these two equations, then delta Q equal to delta phi B by R. So this is nothing but how you're relating the change in flux with the change in the charges. That means how many charges are moving per unit time with how much the flux is changing per unit time. Okay. All right. Okay, so we have discussed Faraday's law of induction and everything. So far we got an understanding that whenever there is a change in electric flux, a current is going to be induced. And so far we have dealt with only regular conductors, like very thin wires which are closed surfaces, and when the magnetic flux changes, a current is produced in a particular direction. But what if we don't have a regular conductor? We just have a very irregular shape or a thick bulk conductor. So when we have bulk pieces of conductors and they are subjected to the changing magnetic flux, again induced currents are produced in them. But their flow patterns are not regular. They resemble swirling eddies in water. So they are called eddy currents. So eddy currents are basically currents generated in bulk pieces of conductors when they are subjected to changing magnetic flux. Okay. So the only difference between the previous case and this case is this current is not very regular. There is no particular direction. They are like random, and that's why we call them eddy current. Consider the apparatus shown in the figure. A copper plate is allowed to swing like a simple pendulum between the pole pieces of a strong magnet. It's found that the motion is damped, and in a little while the plate comes to a halt in the magnetic field. This can be explained on the basis of electromagnetic induction. Magnetic flux associated with a plate keeps on changing as the plate moves in and out of the region between the magnetic poles. The flux changes induces eddy currents in the plate. So when the bulk object is made to move within the magnets, after some time it comes to rest. So why it is happening, we are going to see. So the first step is when the object is moving in the magnetic field, the magnetic flux associated with this particular surface keeps changing, because if you see, if it goes here and there, in and out like this, the magnetic flux through this particular surface will definitely change because there is a change in the magnetic field, right? So in this case, if you look at it, the area is not changing, only B is changing. So then there is eddy current induced in this. Okay. And what happens if you just cut some pieces of that bulk piece and make it like this. So if rectangular slabs are made in the copper plate, the area available to the flow of eddy current is less. So the magnetic moments of the induced currents depend upon the area enclosed by the currents, M equal to Ia. So in this case, obviously the magnetic moment is going to be much lesser. So this fact is used to reduce eddy currents in a metallic cores of transformers, electric motors and other such devices in which a coil will to be wound over metallic core. So why do we want to avoid the eddy currents? Because eddy currents are undesirable since they heat up the core and dissipate electric energy in the form of heat. See, when you have eddy current produced in transformers and all, you will be losing a lot of energy because it just gets heated up and it gets dissipated to the environment, which will be total loss. So we want to avoid eddy currents as much as possible when it comes to transformers. So how do we do that? We can minimize eddy currents by using laminations of metal to make a metal core. Okay. So there are, in some cases, there are some advantages to having eddy currents in the system. So what are they? So magnetic braking in trains. So what we have in trains are, we have strong electromagnets. They are situated above the rails in some electrically powered trains. When the electromagnets are activated, the eddy currents induced in the rails oppose the motion of the train. As there are no mechanical linkages, the braking effect is smooth. So in this case, what happens is, when the electromagnets are activated, when you press the brake, electromagnets are activated and it produces an eddy current which opposes the motion of the train. So the train comes to a stop after some time. And then electromagnetic damping. Certain galvanometers have a fixed core made of non-magnetic metallic material. When the coil oscillates, the eddy currents generated in the core opposes the motion and brings the coil to rest quickly. So this is exactly the example which we saw before. When a metal oscillates between the electric magnetic field, it comes to a stop after some time. We are using the same principle in galvanometer. When the galvanometer needle is oscillating, when we have eddy current, it brings it to stop quickly. Induction furnace. Induction furnace can be used to produce high temperatures. So see, we talked about the dissipation of energy. What if we have an apparatus which needs dissipation of energy as a heat, because we want to heat some objects? Like for example, we have electric heaters in home which uses the same principle like joule heating. But if we want to go to a very high temperature, we can use induction furnace, where a high frequency alternating current is passed through a coil which surrounds the metals to be melted. The eddy currents generated in the metals produced high temperatures sufficient to melt it. So you have a metal and you have some coils around it, and there is eddy currents produced in the metal because of the change in magnetic field produced by the coils. And now this eddy currents are producing very high heat and the metal melts on its own. Okay. And electric power meters. The shiny metal disc in the electric power meter rotates due to the eddy current. Electric currents are generated in the disc by magnetic fields produced by sinusoidally varying currents in a coil. So it also helps to measure the electric currents. Okay. Okay. Now let's see more about what is inductance. So we talked about induction in general. We are going to define what is inductance. So just like, we have defined what is resistance, what is capacitance, inductance is also a characteristic of the material, right? So an electric current can be induced in a coil by flux change produced by another coil in its vicinity, or flux change produced by the same coil. If the geometry of the coil doesn't vary with time, then d phi by dt comes only from di by dt. So the current has to change. Geometry means, we mean the A is not changing. Then if there is a change in the current, then it will produce a flux change. And this flux change in turn produces the EMF. For a closed wound coil of n turns, the same magnetic flux is linked with all the turns. When the flux phi b through the coil changes, each turn contributes to the induced EMF. Therefore, a term called flux linkage is used, which is equal to n phi b for a closed wound coil. So we have n phi b, which is directly proportional to I. So this is for a single coil. For a coil with n turns, then we have n phi b, and we call this flux linkage. The constant of proportionality used in this particular equation is going to be called inductance, and inductance is a scalar quantity. It has the dimensions m l square t minus 2 a minus 2 and given by the dimensions of flux divided by the dimensions of current. The SI unit of inductance is Henry and is denoted by H. Okay, what's mutual inductance? So the word mutual says that there are two objects and they induct, the inductance is there between each other. So two long coaxial solenoids, each of length L, are shown in the figure and they are kept like this. Okay, one inside the other. When the current I2 is set up through S2, it in turn sets up a magnetic flux through S1. The corresponding flux linkage with the solenoid S1 is N1 equal to M12 I2. So M12 here is the mutual inductance of solenoid S1 with respect to solenoid S2. The magnetic field due to the current I2 in S2 is mu0 N2 I2. So this we studied in the previous lectures. So this is the magnetic field produced because of the current I2 in S2. Okay, so that's mu0 N2 I2. So we know that whenever there is a current in a circuit, then it produces a magnetic field, and that magnetic field is given by this particular formula. And this particular magnetic field is going to change, and that's going to induce an EMF in coil S1 which is kept inside. And that's given by N1 equal to M12 I2. So now N1 equal to, let's just see this in detail. What is N1? It's small n1 into L. Small n1 is nothing but the turns per unit length. So this is the length, it makes sense, n1 into L. And what is phi? Phi is B into A. So A is given by pi r1 square because it's the area of this coil, the circular coil inside. So it's pi r squared. And B is given by this. What is the B that is inside the solenoid S1? It is the magnetic field created by the S2, which is given by mu0 into I2. So let's just simplify this equation, rewrite it, mu0 n1 n2 pi r1 squared L into I2. So if you compare this equation with this, if you remove I2, then it gives you M12. So from this we can conclude M12 equal to mu0 n1 n2 pi r1 squared into L. So what is this M12? It is the mutual inductance of S1 with respect to the solenoid S2. Alright? Okay. Now consider the opposite of this. So what about M21? That is the mutual inductance of solenoid S2 with respect to the solenoid S1. So the resulting flux linkage will be of S2 will be N2 phi 2, which is equal to M21 I1. Again we will rewrite N2 I2, N2 phi 2, which is equal to N2 L, and pi r1 squared, r1 is the radius of the inner coil, and mu0 n1 I1. So now if you simplify this comparing these two equations, then what you get is M21 equal to mu0 n1 n2 pi r1 squared into L. So in this case what we are concluding is M12 is equal to M21. So the inductance, mutual inductance of solenoid S1 due to S2 is equal to the mutual inductance of solenoid S2 due to S1. So then we consider M as mu0 n1 n2 pi r1 squared L. In this case, what if there is no vacuum inside, if there is another material with mu r inside? Then we, instead of mu0, we have to put mu r mu0, and then again as usual n1 n2 pi r1 squared into L. So this is about mutual inductance. Now let's see a different kind of inductance called self-inductance. So what is self-inductance? Now as the name suggests, self-inductance means inductance on its own. So there are no two objects here. We have only one solenoid. So the flux in one solenoid due to the current in the other was discussed. In this, it is possible that EMF is produced in a single isolated coil due to change of flux through the coil by means of varying the current through the same coil. So this phenomenon is called self-induction. Flux linkage through a coil of N turns is proportional to the current through the coil and expressed as N phi B equal to L into I. Now L is the self-inductance of the coil. Now instead of M we are using L to denote self-inductance. So similarly, N phi B equal to L into I. So the flux linked with the coil also changes and an EMF is induced in the coil. The induced EMF is given by epsilon equal to minus d N phi B by dt. And N phi B is given by L into I. So we can take L outside since it's a constant. So we have epsilon equal to minus L into di by dt. So what does di by dt represent? It's the rate of change of current with respect to time. So you just have one solenoid. If the solenoid has a time varying current, it's going to induce a EMF on its own in the same coil. So this is what is self-inductance. So the negative sign indicates that the self-induced EMF always opposes the change in current. So this is very beautiful. See, this EMF epsilon is equal to minus L into di by dt. So there is a change of current in the solenoid which induces an EMF which induces the current in the opposite direction to oppose the change. For example, let's say the current is decreasing, then this will be negative, then the epsilon will be positive, then the current will be increasing to refuse the change, right? If you look at this di by dt, what if di by dt is positive? That means the current in the solenoid is increasing. When the current in the solenoid is increasing, the EMF produced is negative. So then the current will be in the opposite direction. So it tries to reduce it. So it tries to reduce the change. It tries to bring the current to the previous value. So what we see here is the circuit, the EMF tries to oppose the change. So whatever change you are producing by changing the current, it tries to nullify the change. Okay. All right. So the self-inductance of a solenoid of cross-sectional area A and length L having n turns per unit length can be calculated easily. So we will follow the same approach which we used before. So we know that a solenoid produces a magnetic field as mu 0 Ni. The total flux linked with the solenoid is N phi B, which is equal to NL, the number of turns per unit length multiplied by the length, and the magnetic field produced by the solenoid mu 0 Ni. I is the current in the solenoid. A is the area of the coil. Okay. So now you have mu 0 n squared Ei by L. So the self-inductance can be expressed as N phi B by I. So if you remove the I from this equation, then you get mu 0 n squared A into L. If the inside of the solenoid is filled with another material, instead of mu 0, you will have mu r mu 0 n squared Ai. So what we understand from here is, instead of vacuum, if you have some other material, then this value adds to this. So that means the inductance will be more. So if you want to have more inductance, you just have to put another material inside. Just like how in capacitance, the epsilon R value got added to the capacitance when you put another dielectric in between. It's something similar to that. So the self-inductance of the coil depends on the geometry of the coil and the permeability of the medium that is kept inside. So if you look at it, there are many ways in which you can increase the self-inductance by increasing the mu, by changing the material inside, and by increasing the number of turns, and by increasing or decreasing the area. Okay. So the self-induced EMF is also called the back EMF as it opposes any change in the current in the circuit. It plays the role of inertia. Okay, this is a very beautiful comparison. So it is like inertia. Like I said before, it opposes any change. So what is inertia? Inertia is if an object is moving, it doesn't want to change. If an object is moving, it wants to keep moving in the same velocity. It doesn't want to change. If an object is at rest, it doesn't want to move, right? So this is nature's inertia. So similarly, if there is a particular current, steady current in the solenoid, it doesn't want to change. Even if you increase the current, the EMF is induced and it tries to reduce the current and brings it back to the natural level. So in a way, self-inductance is like inertia. So work needs to be done against the back EMF in establishing the current. The work is stored as magnetic potential energy. So if you want to establish a steady current, for example, let's say there is zero current and I want to go to a current of I. So from 0 to I, if I want to reach, it is a change in current basically. So the EMF is going to try to oppose this. So if I definitely want current I have to find some way to do work against this EMF, right? So where does this work go? This work is stored as the magnetic potential energy. So for the current I in an instant in a circuit, the rate of work done is dW by dt equal to epsilon into I. So epsilon is the EMF. So we are doing work against the EMF to establish this much current. So it's similar to force into distance. Okay. So you want to move an object to a distance of x against a force, right? Similar to that. So the work done will be force multiplied by this distance. So this is similar to that. You want to establish this much current opposite to this EMF. So it's like this. If we ignore the resistive losses and consider only inductive effect, then using epsilon equal to minus L di by dt, then we can compare these two. Since there is a modulus, we are neglecting this minus sign. So dW by dt equal to Li di by dt. The total amount of work done in establishing the current is we need to integrate this from 0 to I. So we are starting from 0 and we are establishing a current I. So how much work we need to do in order to establish a current I? It is integral of 0 to I Li di. Okay. So if we simplify that, it will be W equal to 1 by 2 Li square. So this is the work done in establishing a current in a solenoid with self-inductance value of L. And this much work done is saved in the solenoid as the magnetic energy. So in the general case of current flowing simultaneously in two nearby coils, the flux lined with one coil will be the sum of two fluxes which exist independently. So current flowing simultaneously in two nearby coils, then you have two inductance values which are M11 and M12. So there is self-inductance and there is inductance because of the other coil. So M11 is the self-inductance due to the same coil and M12 is the inductance on one coil due to the other coil. So if you work on this using Faraday's law, so just differentiate it, then you get epsilon 1, that is the EMF induced in the coil 1, equal to minus M11 di1 by dt minus M12 di2 by dt. And now M11 is the self-inductance, so we can write it as L1 minus M12 di2 by dt. Okay. So now let's move on to AC generator. One way to induce a current in a loop is by changing the loop's orientation or its effective area. So by changing its loop's orientation, we are actually changing the effective area because we know that flux is BA cos theta. So if you change theta also, it is changing the flux. So that's what we mean by changing the loop's orientation. As the coil rotates in a magnetic field, so we have a coil like this, it rotates in a magnetic field. As the coil rotates in the magnetic field B, its effective area A is given by A cos theta. By rotating the coil, the effective area changes. This method of producing a change is the principle of operation of a simple AC generator. An AC generator converts mechanical energy into electrical energy. So how it converts mechanical energy? Because to rotate this coil, you need to provide mechanical energy. And by rotating, you're changing the flux. And the change in flux is inducing an electricity in this coil, which you're taking out by using these contacts. So you're giving electrical energy and in return, you're giving mechanical energy and in return you're taking electrical energy. So this is what I discussed in the beginning of this lecture where I mentioned that this is the basic principles in which we produce electricity in maybe hydroelectric power plants or nuclear plants even, and except like solar panels and all are different, but this is like the basic thing where we use this mechanism to produce electricity in most of the cases. Like even in a cycle dynamo, we use this. So the coil in a magnetic field is mechanically rotated by some external means. The rotation of the coil causes the magnetic flux through it to change. So an EMF is induced in the coil. The ends of the coil are connected to an external circuit by means of slip rings and brushes. Okay, so when the coil is rotated with a constant angular speed omega, the angle theta between the field vector B and the area vector A of the coil in an instant t equal to theta equal to omega into t, omega being the angular speed here. So as a result, the effective area of the coil exposed to the magnetic field lines changes with time, and from that flux at any time t is phi b equal to Ba cos theta, and instead of theta we have Ba omega t. Now from Faraday's law we have epsilon equal to minus n into d phi b by dt. Instead of phi b we can substitute Ba cos omega t. And B and A are constant. A is just the rectangular area of this. So it's a constant, so we can take it out. So we are not changing the magnetic field here. N and S are fixed. So we have minus NBA d by dt into cos omega t, right? So it's like a wave, okay, cos omega t. Now, if you differentiate cos omega t, you get minus sin omega t. So this minus gets cancelled. So you have NBA omega sin omega t. And now this NBA omega, we can take this as epsilon 0, which is like an amplitude of this EMF. So epsilon 0 equal to NBA omega, then you get epsilon equal to epsilon 0 into sin omega t, and instead of omega we can say 2 pi nu being the frequency, angular frequency, then we have 2 pi nu into t. So what does this tell you? If you constantly rotate this with an angular speed of omega, then you get an EMF which is a sine wave, which is like epsilon 0 sine omega t. Epsilon 0 is the amplitude of the sine wave. So the EMF induced is basically alternating. It's like a wave. Okay, you don't get a constant EMF, but you get epsilon equal to epsilon 0 sine omega t. Thank you.
Why waste time in commute and spend a lot of money for NEET UG coaching? Parents, do you want your kids to achieve top scores in NEET? India's leading online NEET coaching, 100% success. NEET UG. TeenEinstein.com. At TeenEinstein, we focus on NEET coaching from Class 6 to Class 12. We think you'll like it. Our teachers are mostly PhDs in physics, maths, chemistry, botany and zoology, with lots of years of teaching experience for Class 6 to Class 12. Thousands of videos, quiz, MCQs. We provide a daily worksheet of 30 questions on each topic: math, physics, chemistry and biology, for rigorous practice, concept understanding, evaluation, quizzes and thousands of videos. Limited offer, 40,000 per year. Book your class. TeenEinstein.com, contact 99402 49720.